So I'm very happy to welcome you to the second seminar in our webinar series that we are jointly organizing with ESReDA, but also with our chair of Intelligent Maintenance Systems and of the ETH Risk Center. And it's also organized together with the Norwegian Center for AI Innovation and DNVJL. I'm happy that we were able to convince Pete Battaglia from DeepMind to present to us today and to share their recent research with us. And Pete has been a research scientist with DeepMind. He has been working on approaches for reasoning about and interacting with complex systems, and a large part of his research has been focusing on graph neural networks. So I'm very happy that he will be sharing his results with us. And maybe similarly as last time, since we are so many, I would like to ask you to post the questions in Slido. I will share the link with you, so we will have also an overview of that. But if you're not able to open it, please feel free also to use the chat function for that. And without further ado, I would like to give over to you, Pete, for your presentation.
Okay, so this talks about structured models of physics, objects, and scenes, which is something that I've been sort of very interested in for a long time. Lately, we've been doing a lot of work with graph neural networks, as I'll sort of mostly focus on today. But I think the broader sort of arc of the work that I'd like to present with that I've done with my collaborators really is about sort of richly structured models of the world. The idea is that if we can learn sort of, or have good forward models, we might be able to solve inverse problems with them. So I won't talk too much about solving inverse problems except at the very end, but that's sort of the general thing we'd like to kind of expand in the future, is using some of these forward models from sort of, to solve inverse problems. Okay. So to start, we often ask ourselves when we're doing machine learning, what tool do I need? So like in the sort of modern deep learning era, it's we often go into our toolkit and we say, okay, well my data is vectors. I'm going to use a multi-layer perceptron, and then we kind of pull up the neural network and Keras or whatever, TensorFlow or something, and then we sort of wire things together, and we maybe do some supervised learning. If the data comes in as grids, we often, the images, we often pull out the convolutional neural network, right? This is a model that operates on grids. And often our data is formatted as sequences, like text or something like this, time series data. So we'll pull out some sort of recurrent neural network, an LSTM or something like this. But the point I like to make is that a lot of domains we're interested in are richly structured. So it's not necessarily clear how to express them as a vector, a grid, or a sequence. So if you have like chemical graphs, like representations of molecules, they're graphs. It's not necessarily always the best thing isn't always to serialize it under some regime like smiles or something like this. You maybe want to leave it and keep that graphical structure intact. And lots of other domains, right? So like biological species, natural language actually, we believe, has sort of some kind of tree or other type of structure that's different than the sequences that it's often formatted as, underneath. Code, everyday scenes, when you look around, you sort of see regions of a room and, a table with a place setting, fork, knives, plate, glass of water. They sort of belong to a little unit that's like the place setting, and then you might see a repeat of these units all over the place. And so the way you understand the world isn't necessarily as some sort of grid representation. In fact, the first thing your brain does is takes the grid of sort of pixel data that comes from the photoreceptors and starts turning it into objects and other types of data structures that are richer than the pixel, the sort of raw input pixels. So in this, when we have a problem or data, or we're trying to create, have a model that generates behaviors that aren't necessarily a sequence of behaviors, but maybe something like a policy that's structured like a tree, like a decision tree or something like this, we can turn now to a sort of popular set of tools that have been developed recently called graph neural networks. and I'll sort of explain a little bit of the background on that, and then show how we use it. So as the background, about 15, 20 years ago now, there was some work by Franco Scarcelli, Marco Gori, and they developed this graph neural network. And the idea was basically to have, it was sort of analogous to convolution over grids, but now we're going to have a sort of convolution over graphs, and sort of a generalization of the notion of convolution on grids or images. And I put here in this slide just a bunch of survey and review papers that I think are good. If you want to sort of read some of the background, there's actually, this slide's a little bit older, so there's actually a few newer ones too. But I can share the PDF of this later, so you can click these links and go check out these papers if you're interested. In my group, we've developed a sort of variant of graph neural networks, which we call graph networks, sort of not very creatively. And the reason we created the GraphNet, as we call it, is the goal was to have it be very expressive, so capture a wide range of different models in sort of related to graph neural networks, but also easy to implement and work with. And at the end, I'll sort of put some links up to some open source libraries that we've released for building graph neural networks, GraphNets. But to understand what a graph network is, or graph, I mean, sort of this is, I think you can kind of look at this as a fairly representative example of a graph neural network. So our GraphNet framework, if you understand that, you should sort of understand graph neural networks in general. So it can take some arbitrary graph, and you can see this graph over on the left is sort of a complicated graph. It's got like multiple edges between nodes. Sometimes there's even like two edges going in the same direction. They're directed edges, self edges. We also have node attributes represented by V, edge attributes represented by E, and you can even have things like a global attribute that's associated with the whole graph itself, which we label U. And so you take these attributes, node attributes and edge attributes, and you put them into a graph network. And the way that works is the first thing that happens is the edges are processed with an edge block, and then you get some computation over these edges, and then that computation is sort of, then you do computation over the nodes and then over the graph level itself, and then you output a set of attributes associated with the graph that are sort of updated. So that's just, these primes are kind of like the global node and edge features that have been computed by the graph neural network. And it's, again, the same structure of graph, but now with different attributes. And I'll sort of walk through this in detail in just a slide or two. But that's the general idea. So you're going to do some edge-wise computation, node-wise computation, global computation. Okay, so here's some work we did several years ago now, about 5 years ago now, on a sort of predecessor of the graph network, which we call interaction networks. And what we were trying to do was basically learn or train models to learn to simulators of physical systems. The reason we thought that was a good idea was because physics is sort of complex. Physics engines, which is sort of how we modeled the architecture, are very general. So you have like physics engines that can apply to a wide range of different physical scenarios. And actually, as I'll sort of show as we can proceed, a lot of the goal of this work was to even come up with single models, learnable models, that could capture a wider range of physical sort of dynamics than any single physics engine. Often physics engines are defined very specifically for the, or they have lots of tricks in them for the specific physical system you're interested in. So I don't know if you're familiar with some of the work by Marcus Gross's lab, probably, and also things like position-based dynamics, where the idea is you're going to have, so you're going to simulate some physical system. You're going to have a set of sort of rules for updating how things should move, like where they should go, and then the physics is sort of computed on that basis. And the goal of some of this, what I'll describe, is to try to instead of having the burden be on the designer to write down different physical rules, what we're going to do is have a model that sort of just can be fit to the physical system on the basis of observing data of the trajectories, and then basically that relieves the designer of the responsibility for writing down the rules themselves, basically. So I'll kind of go through this. Okay, so what we do is so this interaction network. So the idea was we're going to take an n-body system or some physical system, a particle-based system. We're going to represent it as a graph. So here on the left, you've got a little toy planetary system. The blue thing could be like a sun or something like this, and the pink and yellow things might be planets orbiting it. We're going to represent each as a node in the graph. So you can see the colors, the color of the nodes in the graph correspond to the bodies, and then the edges between them correspond to forces, like gravitational forces in this case. So here's exactly how the interaction network works. It's not very complicated. You take for every pair of bodies in the graph, you basically take the attributes of the bodies, that's represented by these V vectors, and any attributes associated with the interaction between them. So in the case of gravity, there's no sort of independent information. It's just gravitational forces apply the same to every pair of bodies, right? It's proportional to the properties of the bodies, not to any independent thing. By contrast, if you had springs between these bodies, now there's this object, a spring, which actually can be like different. So you could have two objects that are connected by a spring with this spring constant, two objects connected by a spring with a different spring constant. So that E could actually vary. So that's why this function here has to take in properties of the interaction as well as the bodies themselves, okay? But you can just think about this phi E as an arbitrary function that's going to compute interactions among bodies. And what it's going to do is then output some latent variable that's just describes something about their interaction. Okay, so that's going to be the semantics of that are going to be decided by the learning process that we're going to train it on. So you can think about this now. Right now, it's just a function that just takes their inputs, bodies, and their interaction between them and computes something about them. And we're going to sweep this phi E function over the whole graph. So I'm just going to kind of like go back and forth across my slides. You can see the blue circle on the graph here is being applied. That represents this phi E function. It's going to be applied to every pair of bodies in the graph. Then we take all the interactions or the messages between them and we pool them up per body. So the body, this blue one here, is going to receive, this node is going to receive the interactions from its neighbors, from the edges that are incident on it, and it's going to aggregate them with some type of permutation invariant operation so that it can then be updated with all the information that's been transmitted to it by its neighbors. So in the case of physics, that's just like forces. We think of forces as transmitting information from other bodies to among bodies. This E bar is like the aggregate interaction of all the neighbors of a body of the node, the blue node. And then that blue node is updated with this phi V function. So this is another neural network. And it takes as input the body's initial state, that's VI, the aggregation of all of its interactions with this neighbor's E bar, and then some global property, like this could be, maybe there's like a force field over the physical system or something like this, that U can represent sort of global global properties. We're going to again sweep this function phi V over all the nodes in the network, which represent bodies in the physics case. And then we're going to aggregate up all the interactions and then update them. So that VI is the update of each node. And we can take this model now. So we've got sort of a set of V primes that represent sort of updates to the bodies that have been informed by their neighbors. And we can do supervised learning to predict for each body what its next state is going to be in the next time step. So if the VIs represent the input state of each body, then the V prime i's could be trained to represent the next state of each body. Okay. So if we take different physical systems, like an n-body system, a bouncing ball system, which is some balls bouncing around among some walls, or a mass spring system. In fact, here's a mass spring system that the blue are kind of masses connected by springs, and the red is also a rigid object. So here there's actually two types of physical interactions, rigid interactions and spring interactions among the entities. We can represent each of these physical systems as a graph. So underneath each image is the graph that represents it. So again, the n-body is a bunch of bodies all interacting with one another. The balls inside the box, they can interact with each other. So the edges represent the possibility of balls colliding. And then this gray thing, the walls are also nodes that are represented in the graph, but they only influence bodies. We set it such that the bodies can't impact the walls. We could have the bodies be able to move the walls, but for our purposes here, we just had it set so that the walls are sort of static. And in the string case, we've got the bodies in the string represented by blue nodes, and the red rigid object, as you'll see in a second, is like sort of influencing, just like the walls and the bouncing balls, it's influencing the string, but it's not being influenced by the string. Okay, so on the top row, I've shown videos of the each of the physical systems. So this is like the ground truth physics engine, the top row of the n-body balls and string. On the bottom row is this interaction network that's been trained on one-step prediction to predict the next state of the physical system. And what we do to create these movies of long trajectories is we just take the prediction of what's going to happen next to the system and just feed that back to the model as input, and then just roll that out like 1,000 times. And that generates these movies. And I'm not sure how choppy the video is on your screens, but if you could see the smoother versions, like the sort of high resolution, high time resolution version, you see like the videos are quite close to the ground truth. So the model on the bottom is very accurate with respect to the top ground truth simulations. The bouncing balls in the center, the states do deviate over time. This is sort of highly chaotic, nonlinear dynamical system. But the key thing is in the bottom row, the simulated bouncing balls by the model it's still a very compelling trajectory. So little tiny errors will accumulate, but it is up. We think that up to that error, it's basically getting the physics right. And we'll sort of go into that in a little bit more in a few minutes. One other thing that's really important about this class of models, these interaction networks, these graph neural networks, is that they generalize well to different graphs. So if you think to how I described the computations, the edge computation and the node computation, I didn't really have to say anything about a graph level computation. There was no function that took in all of the information from the whole graph. All the computations are local. They're like at the level of pairs of nodes or nodes and the aggregated information about their neighbors. What this means is that you can take these trained functions, these edge and node functions, and apply them to arbitrary graphs. So what we've done here is we've just doubled the size of each of these physical systems. So in the top row, you've got movie rollouts of systems that are twice as large as in the previous slide. And on the bottom, the model that I showed you, which was trained on data from the previous slide, is just being applied to these systems that are twice as large. So the model's never seen these systems of, I forget, 12 bodies in the n-body case, I think, or like 30, I think it's like 30 or 25 springs in the mass spring case. It's never seen things that big, but because it's learned the physics at the sort of interaction and object level, it's able to just generalize to larger systems. And we're going to kind of see that as a recurring theme throughout. One other thing we can do is modify this interaction network by adding a third neural network within it. So this is a phi-u function, which is a graph level function that takes the sort of aggregate of all of the node properties. So here now, this vi or v prime is not trained by supervised learning to be the next state of the objects along a trajectory, but just some latent property. Some latent variable, and then what happens in the computational graph of the neural network is you have the v bar, which is the aggregate of the latent node features that are passed to this global neural network vu, and then a sort of updated global property is produced by the model, and we use supervised learning to train that to predict the potential energy of the system. So now we can take this graph, this interaction network, and train it to predict the potential energy of the whole system. And on the right, you just see sort of simple bar graphs that show that the error on the y-axis in the n-body and mass spring system for the interaction network is much lower. The MSE is much lower, so it's much more accurate predictor of potential energy than if we serialize the nodes in the system and feed it into an MLP, a multi-layer perceptron. The reason I don't show the bouncing balls here is because there's no potential energy in the bouncing balls case, so it's always zero. So it's not really an interesting experiment. Okay, so that's sort of meant to give a kind of a walkthrough where some of the learning simulation stuff had come from, and also demonstrate the kind of operations of these graph neural networks when they're used to process and represent and process a physical system. And I'll kind of just go back and walk through in a little bit more detail how the graph networks, and then kind of get to the rest of the experiments. So again, our graph network generalizes, extends this interaction network. So instead of the edge block processing only the E, V, and V the sender and receiver nodes, if it's like a directed edge. It also, now we've augmented it so that the phi, the edge function, also takes in some global context. And this is a sort of small modification, but this just sort of makes it more general. And you can see that represented in the schematic on the bottom left here. The edge block now takes in the U, V, and E, and you can see it's outputting. It sort of has 3 outputs. The set of edges is a copy of the 3 outputs. Go to 3 different directions. They go to update the nodes. They also are given as output, and as you'll see in a second, they can be used to update the global properties of the graph. The node block is the same as in the interaction network. And the global block now doesn't just take in the aggregate of like the potential energy thing I described as global block. It doesn't just take in the aggregate of the node latents, but also the edge bar latents. And that's what this sort of curvy line is meant to represent. These rows are just kind of general functions to represent some kind of aggregation of a set of things. So the set of edge properties are aggregated to update the node and the global. The set of node updates are aggregated to update the global property of the graph. And the reason we sort of did this too was because we realized we could actually capture a whole bunch of other model classes in the literature. So there's message passing neural networks, which by Justin Gilmer. Interaction networks are one example. Graph convolution networks are another example. That schematic would look like this. So I don't really expect you to kind of see all the details, but the key thing to get in this slide is that a bunch of different models, message passing neural networks, non-local neural networks like the transformer, deep sets, or the relation network was something that we worked on several years ago. You can kind of see that they're all basically cookie cutouts of this general template, this graph net. So you have this graph net. If you remove some of the connectivity in here or some of the components, you get these other models. So you can kind of view this as a generalization or unification of a bunch of these different models. And as I said before, the sort of easy to implement, easy to work with idea, we realized that all of this model can just be viewed as a sort of graph to graph sort of function. So you have like this interface. As long as you pass a graph in and you get this graph out, you can wire these things up in different ways, and you can have different graph nets with shared functions or unshared functions. So on the left here, you have like sort of I think I mislabeled this. The shared core should be at the bottom. The shared core is sort of at the bottom. The unshared, you have like GN1, GN2, GN3, different models, different parameterization. So the top row is sort of like a deep convnet, basically. You have like a bunch of different convolutional layers with different functions. The bottom is sort of more like a recurrent, or like, I guess like the bottom, sort of a recurrent model. Or on the right, you can kind of view, like if you actually take graphs as input, maybe you're tracking some physical system, you actually have some hidden graph state that can be merged, with an encoded input graph state, things like this. So you can play all these games people play with deep learning, compose more complex architectures. Okay, so then we started to apply these models to other types of systems. So like these control systems. We wanted to see if we could learn physical simulation, not just over these kind of simple 2-dimensional things, but 3-dimensional things that people in robotics care about. So we use the DeepMind control suite, which is something that was released by DeepMind. It includes a bunch of different control systems. And actually, we also applied this to some real robot data. It's the same story as before. You take the physical system that's represented in the DeepMind control suite. So here it's some kind of like 2-dimensional cheetah thing. We represent it as a graph. So here the bodies are represented as nodes. The joints between them are represented by edges. And if there's any global properties, you can represent that as well. Here's on the top I'm showing is how we're starting to kind of wire up these graph network blocks in more complex configurations. So we have a sort of dynamic properties of the input graph, static properties like mass. They're concatenated together, given to a first graph network block with a set of parameters. There's also a skip connection around that, and then that goes to a second graph network block with a different set of parameters to predict one step, the next graph. And on the bottom, you see a video of, on the left, the ground truth, the right, you have the prediction of the model. There's just been random control inputs given to this little swimmer system, this sort of sequence swimmer system. But what's interesting is you can, so that again, we can play the same game, we can simulate the swimmers. We can also take a single model and train it on a bunch of different systems. Again, because it doesn't, the locus of learning is at the edge and body level. It doesn't really know about the global structure of the graph. So we can take graphs that have different structures and train a single model. So you're seeing in the top row, the single model, it's trained to produce the dynamics on the, of all these different systems. And we also get the same kinds of generalization patterns I was describing before. On the bottom, you've got a model that was trained on swimmers with 3, 4, 5, 6, 8, and 9 links, and then we're testing it on swimmers with 7. My video is not actually moving. I'm not sure why, but I'm not sure if you can see it. But oh yeah, they're starting to move. We tested on swimmers that are have different numbers of links than it was trained on, and it sort of works. Although it does sort of degrade as you get to much larger swimmers, because we think there are sort of global properties of the system that start to the statistics sort of change the dynamics. The model might not be equipped to sort of these are neural networks, so they sort of operate in a dynamic range they've been trained on. Okay, and we can keep scaling this. So this year, or last year, I guess now, we've continued playing this game. Now we said, okay, instead of 3D control systems with say 15 bodies or whatever, how about fluids with thousands of particles? So here we can represent a fluid with as a set of particles, and then we're going to train a simulator to predict its dynamics. And we're doing the same thing. We're always going to train on one-step prediction, and then we're going to roll this out by just feeding its predictions back into itself as input. Here's the architecture that we've sort of now kind of consolidated and settled on in a lot of our work, this encode, process, decode system. So the encoder is actually, I have the next slide, yeah. So we construct a graph by taking the set of particles, creating edges between particles that are neighboring each other. So this gray, sort of faint gray circle is meant to indicate a neighborhood around this particle, and we attach edges to the other particles that are in that neighborhood. It's just sort of a sparse neighborhood, kind of topology. And then we pass messages among the nodes by running them through this a sequence of unshared GraphNet blocks that have residual connections. So the idea is we take this graph that we've constructed, we feed it into a GraphNet. It makes a prediction, and then we have a residual connection where it adds its prediction to the embedding. Actually, I forgot to say, this encoder has a little graph network here also that embeds these particle positions into a higher dimensional latent vector. So we take that high dimensional latent vector and sort of update it sequentially 10 times. I think m equals 10 typically in these experiments. Kind of a sequence of unshared GraphNet blocks that process the system to compute the dynamics in the next step. So we have 10 steps within a single time step. So 10 internal kind of sub-steps within a single time step. And then we take the latent vector that's been sort of generated by this stack of updates, and then we decode it into something like the change in position or change in velocity, and then just do an Euler integrator to update the state for the next step. And when we do this, so here on the left, we've got ground truth video of some splashing water. It's not that, hopefully it's not too choppy on your screen, but you can see on the left, we've got this water simulation. I'm going to kind of fast forward it. So the reason it has a kind of surface is because we've just post-processed it and added a kind of surface onto it, but it's going to transition now to the actual particle representation. So you'll see what the underlying representation of the particles in the graph are there. So there's the particles. Oops, that's very choppy. Okay, so that you can see the particles. So on the left, you've got the ground truth. On the right, you've got the GraphNet-based learned simulator. And it's a very faithful representation. You can see it gets that splashing behavior very, very accurately. This was 14,000 particles. The ground truth simulator was smooth particle hydrodynamics. We can also go beyond water. We can do sand. So here's our sand. My video is very choppy, so it's got to be choppy on your screen. I'll just kind of try to click forward to the particle representations. So here's the particle representation of this sand. So it has a different material properties simulated with a different simulator. Here's 19,000 particles. This is a material point method for the simulator. So the same architecture, it's trained separately on water, sand, and the next video you'll show you the goop. So this is our goop material. Again, we just changed the sort of the material parameters within the ground truth simulator, train our model on it. But it's the same architecture that can be trained on these different systems. And I'm going to show you in a second, we train single architecture on all of these different materials at once. So we can also have the particles interacting, we can simulate things. Sorry, my video is really struggling, I'm not sure. Okay, so we can have the fluid interacting with rigid things like walls. You can kind of see it's like flowing through these obstacle courses. And this one's the one I'm sort of most excited about. So we can actually simulate with this a model multiple materials. So now we give the material properties, we just sort of have those as attributes of the nodes that are being passed to the model. So now we've got, I'm not sure how to chop. This is very choppy on my screen. I'm not really sure why. But hopefully you can kind of see that now you've got water, sand, and goop interacting with one another. And in fact, this is a very, this one was actually not just meant to show that we can have water, goop, and sand interacting with each other, and we learn to simulate these sort of very complex dynamics. But actually the training for this, which I'm not showing here, is a much smaller box, is much simpler interactions among materials, and much shorter trajectories that it was trained on. So this is really starting to demonstrate that we can generalize to much, much larger, more complex and longer sort of dynamic, trajectories than the training data even contains, which is exciting because it opens the possibility of having like training models on very well-controlled small scale things and then running them at very large scale. And I'll kind of show a little bit more of that in a second. One other thing we can do is we can even simulate rigid things. So here you've got a green cube that's represented by particles, and we've just indicated to the, you've given attributes to the green particles in the graph that they're rigid things, rigid particles, and then the simulator on the right just simulated, the left is again ground truth, the right is the prediction. The prediction, you can see it really holds this box together very well. And this was actually fairly hard for us to get working, but now I think, if you read the paper, you can kind of see the different things that were required. But a lot of it has to do with sort of how large the radius around the particles is, how we do the updates, and then give them to the integrator at the end. Okay. And so the last thing in this kind of little sequence of experiments, I'll show a few things afterwards that are a little bit different, but the last thing, this is very recent, this is going to appear in iClear in I guess like a month or two now. So we continued sort of pushing these classes of models. Now, instead of just fluids, we're going to do non-rigid materials. So we're going to represent the system as a mesh. So we've got 4 different systems here. We've got these cloths that are kind of blowing in the wind. We've got the structural mechanics where there's like a metal plate that's being pushed by some kind of rigid actuator. We've got compressible and incompressible fluids, so like air and like water. There's like sort of airfoil and like this kind of cylinder flow. This is almost, again, this paper is, we're not that creative. It's sort of working. It's we're just sort of applying these things to bigger systems and more complex systems. So it's a similar idea. So we're going to take the system represented as a mesh, just like the underlying simulator does. And now we're going to train a model to predict the next step of the system. A key thing here is we've got 2 types of edges now. So now we have the sort of mesh space edges, which are like the things that are like, it's a cloth. It's like the edges sort of represent the sort of solidity of the material, right? So the cloth is, it's like a sort of non-rigid solid, and the mesh represents that, so that the mesh, like the cloth, always stays intact. Even if it deforms, it stays intact. But then we also need to be able to simulate the cloth having self-collisions or other objects colliding with the cloth. So we have a second set of edges that are computed on the fly, and they're like based on the local geometry again, as before. So before in the particle thing I showed with the fluids, all the edges had to do with, were just computed from proximity. Here we've got 2 types of edges. One has to do with proximity, and one has to do with like something that represents the solid connectivity of the material. But it's the same basic idea. And one key thing about this, which was very exciting for us, was that when our model is roughly 10 to 100 times faster than the simulator on which it was trained. So when we just run out steps, we're running on TPUs and GPUs and things like that. We can run them about 10 to 100 times faster than these highly optimized sort of graphics and structural engineering simulators. So here's some examples of the results. So in the cloth on the left, you got the ground truth again. On the right, you've got the prediction from the model blowing the wind, and you can just see that the model is very, very accurate with respect to the ground truth. It's not a perfect reconstruction of the trajectory. There is a little bit of noise that accumulates, but again, the thing is that it's still very, it's a very plausible trajectory. It doesn't explode, it doesn't tear, or things like this. I don't think I included any of the, when you parameterize our model in poor way, you'll see the cloth just kind of like ripping or shearing or forming all kinds of crazy shapes if it's not accurate, but here it's very accurate. One other thing actually I had forgotten to mention was we do some, we also have learned remeshing. So a lot of these modern mesh simulators remesh the mesh online to get more accurate sort of numerical approximations to the dynamics. And this can be very helpful in engineered simulators. We have this other component in here also where we're actually learning the remeshing. So instead of just taking the input mesh, we actually learn to change the mesh connectivity to have more stable simulated dynamics. Here's the structural mechanics. So on the left is ground truth, and the right is the prediction is the model. And you can see it's sort of almost perfectly accurate here. And then here's the compressible, incompressible fluids. So on the left, you get your air, and again, on the right, you've got your water, and you can see that they're, again, the colors represent, I think they represent the velocity. Is like the norm of the velocity. So the state here is like the pressure, density, and like the sort of velocity, local velocities. And here's the kind of how this model can generalize again. So it was trained on that flag that I showed you before. We can create different types of cloths at test time, and then with different meshes, and then the model will still generalize to them. On the left, or the right here, you can see we inset how big the training mesh was alongside what we're showing at test time and generalization. So you can see it's a much more complex mesh. Much larger. It's got these kind of like tail things and this funnel windsock deal. And again, just meant to show that the model generalizes beyond its training. So this is exciting, right? Again, we're training on small things, we're generalized to much larger things, and the model is 10 to 100 times faster than the ground truth simulator. So again, we're really starting, we think we're kind of open to the possibility of doing things that traditional simulators can't do, maybe. Just by training on little local regions of if you take a ground truth simulator, train on a little local sort of simulation from it, and then just do it at scales and speeds that it can't operate on. Okay, so that's the end of the sort of physics part. Let's see how am I on time. So 10:40. Okay, so I think I started about. So I'll do maybe another 5 or 6 minutes. Okay. So now I want to switch gears a little bit. So we were just talking about meshes and simulating meshes. Now I want to show some work that we had at ICML this year where we're generating meshes. So this is work by Charlie Nash, and I'm going to describe an autoregressive generative model of a 3D mesh. So the kinds of meshes are going to be these like kind of everyday objects, chairs, dressers. And the way we represent them is as OBJ files. I should also say the side point, Charlie Nash, who's a great researcher in my group. I think part of his research program can kind of be described as taking file formats from the 90s and then training models that operate on those descriptions. So we just submitted a paper to ICML where he's now done this with a sort of like variant on JPEG files. So we've got like our OBJ files or JPEG files, and I think maybe, I don't know if we're going to go to MP3s next, but the idea is that we're taking these good, well-engineered data structures for raw data and then just modeling them directly instead of trying to model them on like the basis of the pixels or on like volumetric representations. So again, this model is going to operate on OBJ files, a set of vertices, and then a set of faces. These are the indices of the vertices that need to be connected. So in this cube, it has 8 vertices for each of the corners. And then these integers indicate which corners are connected to one another and comprise the faces. So each face has 4 corners. And the way his model works, so now it's not a graph neural network, it's a transformer, which is quite similar and related. So the transformer, you can kind of think about it as, it's almost like learning to the edges. It's like learning to predict soft edges on the fly. So rather than giving it edges as input, it's computing interactions between all the particles or nodes in a set and then weighting its messages in proportion to the interaction strength. So it's, again, so you can think about it as like a sort of soft, it's inferring the graph and doing the message passing. That's kind of the way I think about transformers. So what Charlie does is he's got two transformers, a vertex model and a face model. And what he's going to do, again, it's an autoregressive generative model. So the way it works is it generates some stuff, and then it conditions on the stuff that's already generated to generate the next stuff. So it sort of predicts the first thing from scratch, and then conditions on that predicts the next thing. And those things are vertices and then faces. So like I said, he basically just goes right down this list. He just serializes this whole thing, 0, 2, 2, 0, 0, 2, and then like the faces like this. And then that's the transformers just walk through it straight through like that. So you can see this is meant to represent the green is the conditioning on the previous vertices that have been generated, and then it predicts a new vertex. And on the right, the face model is taking the vertex, conditioning on all the vertices that have been generated. So the list of vertices and the indices of the faces that it's already generated. You have to read the paper to know the details. There's a pointer network in here, which is used to actually predict the indices. And you can see it's sort of constructing a new face, and this is kind of meant what this sort of red dotted dashed lines, and then the kind of solid face is representing the next face being generated. I won't go to the details, but basically here's what he can do is he can do class conditional samples, so he can condition a class like lamp, sofa, clock, cabinet, jar, bench, monitor, chair, table, and he can generate meshes. So the data set was ModelNet. Or ShapeNet, I get confused. They're related. Is it ShapeNet or ModelNet? He trained it on these data, just like they trained sort of large-scale language models, but here it's meshes, and he can do class conditional samples. So you can kind of when you do like GPT-3 and you condition on some little piece of text at the beginning, here you're conditioning on like a single word. He can also condition. Oh, I didn't show this slide. Oops, sorry. There's supposed to be one slide in here that I must have forgotten to put in. He can condition on images, so you can actually take an image, embed that, and then generate meshes that are consistent with the image, and that's basically like a kind of visual system, basically. Here's the model in action. So here you can see it generating the vertices, and then it's going to generate the faces. So on the left you got a lamp, then you got the middle you got a couch. On the right, you've got some kind of vase thing. The way he serializes the vertices is just from bottom to top. So that's why the model kind of creates the thing from the ground up. Cool. Okay, so yeah, since I'm out of time, I'm basically out of time. So I think I wasn't sure if I was going to show this, but let me just show you one kind of punchline from this. So the idea of all this work was we're going to train models to do physical construction. So here, yeah, this is the key slide. You've got a scene. So this black thing is the floor, the blue thing are blocks, and the red thing is this obstacle. We represent that scene as a graph, and we're going to train a policy by sort of Q-learning, so that it's got a Q. So this is like an RL problem. We're going to train an RL agent to construct block scenes. So if this is a little block scene, it's got to place more blocks in the scene. It's going to do this by modeling the value, the state value function over different blocks. So it can say, I'm going to place blocks that in the scene, like this D block, I'm going to pick it up off under the floor, I'm going to place it on top of block B by predicting relations between blocks. So I know I'm not getting into the details. You can almost think about it like Legos, though. It's like you got these blocks. Should I snap block, a block onto this block? Yes, and like it predicts at the base on the basis of like interactions among the blocks. And we can do sort of model free or model based. I'll just kind of show a cool video of it working. So this is, in this task, its job is to, actually, here, let me show. In this task, its job is to take blue blocks from the bottom and create little shelters over the red blocks. So these red blocks, it can't touch the red blocks, but its job is to kind of cover them up in the rain, for instance. So it's got to stack the blue blocks to cover up these red blocks, protect them from rain. These little gray things you're seeing, it can choose also to glue blocks together. It pays a cost for glue, so it shouldn't use glue on everything, but when it needs glue, it'll use glue. And it's creating little houses over these red blocks, basically. But again, it represents this scene as a graph, and it's learning a policy that's defined by a Q function, a state value function, on the interactions among the objects, where to snap blocks together. Okay, so now I'll close. So I just want to sort of give a little pitch for, we have two libraries. If you want to use our open source libraries for building graph neural networks in TensorFlow. You can go to this GitHub link. It's on the DeepMind thing. So graph_nets library. We also just released a new library. We've all sort of kind of moved to JAX now. So JAX GNN library, which we call Giraffe, JAX, Graph, Giraffe. We have lots of examples here. We're kind of adding to this right now. So hopefully there'll be even more kind of demos and things like this. But this is the one we're mainly using now. And that's basically it. So my conclusions, the main thing I want to say is, graph neural networks and transformers, very powerful architectures for reasoning about rich and complex structure, especially like the physical and scene, physical systems and rich objects and scene. Again, learned message passing can support complex physical simulations. It can represent and reason about structured objects and scenes, and it can drive construction behaviors. And if you want to mess around with any of the you want to build your own graph neural networks, play these, do these types of things, you can do it with our libraries. A lot of our code we've been open sourcing. Hopefully we'll be open sourcing some more soon too on the actual research, like on the papers. And that's it.
Thank you very much, Pete, for the very interesting and very broad presentation. Thanks for touching so many different topics and giving examples on it. Very impressive, very interesting. We have quite a lot of questions. I will just start with those that are at the top, and then we will see how far we will come. The first question is, how much would you trust the graph networks for safety critical systems? So would you advise to use them within control systems, since they were quite close, but not very close to, or not particularly precise for some of the applications? So what would be your comment on that?
Question. I would, I mean, I would trust them as much as I would trust any other neural networks. Right. So like, I think if you, it's not really about the model as much as I would say the, like the testing, how you kind of verify that that it works. One thing I will say though is, we had a collaboration a few years ago with some people. So I'm at DeepMind, and we're sort of part of Google. Collaboration with some Google teams on from Google Maps on traffic time prediction. And so we actually built some travel time prediction models, and then they were very effective and they're very robust, and they were rolled out globally. Like if you go and check the travel time to from some location, from where you are on your phone on Google Maps, it's going to give you a prediction that comes from our GraphNet library. So it's been rolled out, I think, everywhere. Google Maps, all the traffic worldwide, they're making predictions about travel time, and it's much, it's more accurate than the previous system. It was a sort of the thing that Google had tweeted about this, I think, last summer too. So I think that's not really, travel time prediction isn't about safety, but it does show that the model is very, these approaches are very, capable of working in production systems, sort of robust. And I don't know if that sort of helps. But
I've also tried to quantify the uncertainty of the predictions that you do.
Yeah, that's a good question. There's no reason. So we haven't explored this as much as we should, and we actually like to explore this more. We are starting to explore this more now. So I think there's sort of two ways you can think about this. So one is a kind of like, predicting. You could do like predicting confidence intervals or like distributions around your predictions, right? So instead of modeling the, I should say in the stuff that polygen thing, generating the object meshes, that was a generative model. It was a distributional, predicted distributions over the pixels. So you actually did have, or over the vertices and bases. So you did have distributions that were being predicted there. So you can model the distribution of what's going to happen rather than like sort of point estimates like we're doing a lot of the simulation stuff. That's the kind of like shallow way to do it. The deeper way to do it would be to actually have these be full probabilistic models. So make them make them latent variable models and have distributions throughout the whole thing. So instead of just like a sort of model that's predicting a distribution, you have like, trained like a, variational autoencoder training or something like that, or a normalizing flow. Yeah, but we haven't explored that as much as, it's kind of funny. It's a little bit underexplored thing in the whole graph neural network literature, I would say.
Okay, thanks. There's another question from Chow. Any suggestion if we do not know the true edges in advance and need to learn these edges? So how would you go about that?
Yeah, so Right. So the answers I would give are that. Okay. Actually, let me make a sort of point that I think is pretty important. The edges, they actually play two roles. So I didn't say this before, but the first thing they do is they carry information about the structure of the input. So for instance, like if it's a mass spring system, the edges might represent there are springs between these particles. But another thing they do within the model is they are the mechanism for passing messages through across the system and allowing the interactions among things to be computed. And again, like even though we have sort of local pairwise interactions that are computed, we often stack multiple sub-steps, so you can kind of propagate information beyond just like your immediate neighbors. To, you know, if you have 10 steps, you could go sort of 10 hops out. So, but the key thing again is the edges represent the structure of the input as well as they're used to perform the computation. And I don't see any reason why the message passing edges inside should actually correspond to the input edges. So in physical systems, it sort of makes sense because the interactions often represent like, it's kind of like forces. Like we can kind of simulate a physical system by, how forces kind of propagate. But if you have some, social network or something like this, and the edges are just like, who's liked this or who's friended this, right? The people, the nodes might actually be connected by things that aren't represented in the input edge. So I think this question is really important, like this question of how should we decide the edges? And again, it's not only just how should we decide about the edges that are out in the world, but how should we decide on the edges that we want to use to communicate within the sort of, like through message passing. So the things I'll say is transformer, as I mentioned, it like has sort of this learned edge, soft edges. So I think that's one answer. The problem with that is that in the limit, it's sort of quadratic complexity. So if you have a set of 100 things, you're going to have 10,000 interactions you need to compute to see which of those 100 things interacts with which of those other 100 things. Now, there have been the last year or two some more efficient transformer architectures like reformer, linformer. There's this random features attention. So people are starting to exploit things that have been sort of studied in graphics and engineering for like decades to optimize these sort of computations and not have to do the full quadratic sort of interaction computation. But yeah, I mean, that's really one of the only ways you can sort of explicitly, I think, predict, learn to infer edges. But the one other thing I'll just add is that it's not entirely clear to me that you need to get the edges correct. Because like I said, when you do a bunch of steps of message passing, you're going to propagate information over the graph. So like, yeah, even if you didn't get the edges just right, you really still will be able to have things communicate that aren't connected by edges. It's just going to take several hops. So I think that these questions really should be sort of actively studied, like how to really optimize the computation. But I think the answer that we learn might end up being, well, you don't really have to get the edges right, or there is no right in some sense. Ultimately, what you want to do is just allow the produce, have edges within the graph that allow you to solve the problem that you're trying to solve, like optimize whatever you're trying to optimize. I hope that I know that's kind of a long-winded thing. I hope that kind of helps answer it.
Thanks a lot for this answer. There's one other question from Harvey. Why not learn inverse problems directly instead of learning forward simulations? Any ideas on how to deal with problems that can't be fully observed, maybe based on neural networks?
I didn't get into I mean, in some sense, like, I'll just show this slide again. Like here, we're actually, this is the model-free method. Again, I didn't describe it, so it's going to be hard to kind of like make sense of it. You also have to sort of trust me. We did have a model-free version that's actually, you can kind of think about it as trying to learn the inverse problem directly. It's sort of just trying to map directly to not a policy, but the values, the Q function that can be used, part of the policy effective. But then we also have a version that uses MCTS and has a model. So here we actually have a model of the sort of physics of this little environment. And what happens is we compute a Q function by rolling out forward trajectories. So this can be viewed, it's a Monte Carlo tree search. So it's the Monte Carlo method to sort of infer what the Q function is. So I don't think that there's necessarily the inverse problem. I mean, there's plenty of people who are using graph neural networks to solve, you know, in a sort of discriminative regime, right? It's sort of like trying to learn the inverse problem directly. I just personally, I've just been very interested in generative approaches for a while. So I also sort of think that a model, I would say we've also kind of found that models, I believe that if models can simulate the forward dynamics, it's kind of a funny question, right? Like you can simulate the rich forward dynamics of some problem. Is that harder than solving an inverse problem that is only sort of related to one small part of the forward process? I think it's sort of a problem specific question, but like I think we often find that if we often use physics because we feel like if we can capture the dynamics of these complex systems, then we can capture lots of complex functions, even the inverse map of some problem that we care about. And I think even like with things like the travel, again, the Google Maps travel prediction, we're training models of like flow and networks and fluids and things like this, and then we're trying to map directly to travel time prediction. One could try to train a simulator of traffic. I don't know which is harder, train a traffic forward simulator or just try to predict traffic, travel times directly, things like this. Yeah, so I think it's an open question. I think we should solve the inverse problem directly and indirectly with generative approaches.
Okay, thanks for that. There's a bit of a related question to that. So, because you were relying quite a lot to have a full observation of the system and then learn from it and then covering all the different conditions, or you were simulating. So what if you don't have both? So if you don't have this rich observed data, or if you don't have the simulator available where you could simulate all the different conditions?
So I think this is, again, like I started to touch on some of these things, like in the mesh thing, which is the slide that I didn't put in, which is going from the image and conditioning on the image and then predicting the mesh. But even there, the training, you had the mesh. But like, yeah, actually, I think this question is very related to the question from like 2 questions ago about the what if you don't have the edges? It's like in some sense, if you just have some raw data, but you don't know what this underlying structure is, you have to sort of infer it, right? So I think that actually the question of if you're going from real data where you don't necessarily have like some kind of full symbolic pristine state, that's what you need to do is, to use these types of structured models, you need to infer some structure.
But in real data, you may not have observed all the different combinations you may need to learn. So that's also why you were using some of the simulators. So what if your data is limited or maybe it's limited to just one part of the representative?
Well, what do you mean all the different combinations? Yeah, what do you mean by, like you said, like all the different combinations, but what do you mean exactly? Like you mean just small data? It's small data neural networks, deep learning and small data.
Yeah, well, you can also observe the same state for quite a while, for example, and then not have too much variability in your data. So possibly this is what I mean, right? Because you're trying to learn kind of different combinations and different interactions, different dynamics. So what if your data does not represent what you're actually trying to learn? And also this is why you're using the simulators or partly, and this is the reason.
Yeah, I mean, that's a good question. I think there's 2 things you could say. One would be you might want to try to do like domain transfer, like sim to real style things where you have like this, like, kind of, what do they call them? Data assimilation, things like this, where you have like a simulator, you have like, or, things where you basically kind of learn from a simulator, but you have some way of transferring to real data or like kind of fine tuning real data, or things where you have like underlying simulator that's being updated by like real data as you track or something like this, data assimilation. So that's one thing I would say, like you could explore things like that. The other thing I think is that I would say though is that these models tend to be more. I think that the reason these models tend to work pretty well in like these things is because they do a lot of sharing. So they're like for the same reason that CompNet is more efficient than like sort of an MLP for learning like image processing, because it can share a local function everywhere in the image, and it can sort of like take all parts of the image and fold that onto itself. So it's sort of almost like if you have like a kernel and you can sweep it over the image into like 100 different places, it's almost like you have 100 times as much data in some sense, like in kind of loose sense. Here, by convolving, again, these little edge functions, message functions, convolving them, or no functions, convolving them over a large graph, you might be able to learn from small amounts of small numbers of graphs. because again, you're sharing that learning all over. Like in principle, you could learn from a single graph if it were sufficiently large. If your computations were sort of like about local parts of the graph, and we've kind of explored this a little bit. But I think in general, your question is really broader than even graph neural networks. I would say that this is just a general problem for neural networks, which is like, you're really stuck to the dynamic range of the statistics of the the data and the representations you've been learning. So if you try to generalize beyond that, you're in trouble. I mean, and I kind of would think we want to go toward more like stronger inductive biases and things like this supplement our lack of data with other sorts of knowledge that we can rely on. But I think this is a good question for all of us, really.
And there is maybe the last question, which is quite related to that. Can you comment on the extrapolation capabilities? Because you were trying to transfer it to things that you did not train on. So what is in general the ability, but also the extrapolation ability of the models that you were using?
So I think, I think you can think about extrapolation in space and time generally, but like at least these physics models. The time extrapolations, it seems to be very good these days. Like we've got sort of, I think we have some probably like kind of accrued wisdom about how to get long-term stability in the rollouts, even from training from one-step predictions. A key thing that I cannot emphasize enough that we still don't completely understand is, but you want to corrupt your inputs with like a little bit of noise, and that seems to make things much more robust to long-term extrapolation. If you're interested in sort of we've kind of been studying this internally. We haven't published a paper on how this works because we still haven't quite figured out why exactly it works, but it does seem to work almost all the time in everything we do. If we add a little bit of noise kind of in the right way. So especially in the ICNL paper on the particles from 2020, we did go into some of this noise manipulation. So if you're interested, you can read that, but feel free to email me. So that's the kind of time thing. I think like they extrapolate very, very well from one-step training to like very long trajectories. Spatial, like larger systems, extrapolating. The answer I would say is if the local dynamics of the larger thing are like the local dynamics of whatever you're training on, the small thing, I would sort of cautiously be optimistic about its ability to generalize. Like now we are seeing that we can go to systems that are typically about 40 to 50 times larger in like number of particles in spatial kind of like domain than what it was trained on. So yeah, I would say 40 to 50 times larger. One other thing we often do is we make things translation invariant by, instead of giving absolute positions, we give relative displacements between things. So instead of having two particles have their absolute positions go into the edge function, we'll take the displacement vector between them and make that an edge attribute and give that to the model. So we do things by like forcing the model by construction to be translation invariant and things like this. That can help. There's some nuances to get that to work, right? Because sometimes you think you're making it translation invariant, you're not, because you have something in the scene like a wall that's always in the same position. So the model could learn to use that as its coordinate system. But there's also a lot of work that's happening now, I think, we're starting to do this with other people. There's these like Stefan Gunneman has got some really nice work on these like rotationally equivariant models, and they're thinking about like even kind of group invariances and things like this to try to really improve the generalization capabilities, which actually seems to be quite successful and exciting right now. So I'd sort of point you to that.
Okay, thank you very much, but also thanks for sharing these insights on the extrapolation capabilities and this noise addition.
Someone, just to say, someone on this questions asked if I'm going to share the slide. I can share those. So just let me know how you want me to share those, and I can. Okay,
sure. Thanks. So, thank you very much. And so the next seminar will be on the 19th of March, and yeah, join again for the next seminar. Thanks a lot, everyone, for joining, and enjoy your lunch.